Can you hear me, please?
Yes, sir.
Good. Are you awake?
Yes.
Good. Let's start to the problem. As I mentioned, I will not cover a new material. We are going today and Thursday, we are going to go an overview of what we have learned. We went through it. Therefore, I prepared 4 questions for today, and I would like to give you a chance to practice for the rehearsal. Every problem I give you 10 minutes. Please take a pen, pencil, and paper and write your solution. The idea here is for you to practice and learn where you are making mistake. That's the whole idea of this exercise, is not giving you the solution, because I can give you the solution, email you the solution, no problem. But here is trying to find out what is the depth of your understanding. Are you ready? I will take it. Can you see the screen?
Yes, sir.
Good. Let's start the first one. Okay, that's the problem. Consider water pipe of length 17 meter. The diameter is given for inside and outside, and thermal conductivity is given. Heat is generated in the pipe, in the material of the pipe, not inside the pipe. Therefore, the thickness of the pipe, there is a uniform generation of 25 kilowatt. Okay? The inner and outer surface of the pipe are at 60 degree, as 80 and 80 degree. Obtain a general relation for temperature distribution inside the pipe. It means inside the thickness of the pipe under a steady state condition, and determine the temperature at the center of the pipe. Okay, therefore you have a thickness of 5 centimeter, because inner is 15, outer is 20. Therefore, we assume the thickness is 5 centimeter. I would like to calculate the temperature at the center of that one. Please take your time. I keep track of time here, and let's see how far you can go. To be sort of helpful, you can have your formula sheet, but please do not look at the textbook, okay? Just start from your formula sheet. You see how useful is that formula sheet, or is it any information is missing? That's also, again, another part you can find out what is exactly you have to add to your formula sheet. If you have any question, please ask. let me start. Any suggestion how we should start?
Well, first, it's chapter 2, so we can use the equation for steady state with heat generation,
Okay.
assuming K is constant.
Okay.
Yeah.
Therefore,
So
you're assuming this is cylindrical coordinate, right?
yeah, long cylinder. Yeah.
Yeah. Okay. Let's start with that one. Therefore, you start with this equation. It's a steady state. That's correct. And since conductivity is constant, you can take it out, and this equation reduces this one. Therefore, you have conduction through the thickness of the wall of the cylinder, and you have also heat generation. Now, if you go back to the problem, we have the radius, we have the length, and conductivity of the material, and mention heat is generated in the material uniformly is 25 kilowatt. But if you look at this equation, this generation is per unit of the volume. Okay, then we have 20 kilowatt. This is per unit of volume. Therefore, now we have two boundary conditions at R equal 15 mention what is the temperature, and at R equal 20 also mention what temperature. Therefore, we integrate this equation. This is the one boundary condition that we have, and this is the second boundary condition. Therefore, we know the radius of the pipe at 15 and 20. These are the temperature, and also this mention about the heat generation per unit volume. But the value of given to us that 25 kilowatt is mentioned kilowatt. What should I do now? Because mentioned that the energy generation within the pipe is 25 kilowatt. But if you remember, this unit of this energy generation was energy generation per unit volume. Okay, this was per unit volume. Therefore, we know the dimension of the pipe. We know the length of the pipe. That's why given here. It mentioned 15 meter. It mentioned this is the, therefore we can calculate what is the volume of this mass that we have. 5 centimeter thickness and 25 this one. Therefore, we can go and calculate the volume of that one. Therefore, here we have this is energy generation kilowatt, and here is the volume of the pipe solid part. Therefore, this is exterior, this is interior, and this is the remaining become the thickness times L become the volume. Therefore, now we have this is 26 kilowatt or 26,550 watt per square meter. Therefore, that's not this is my heat generation. I can replace this one here and integrate the equation between these two boundary conditions. Okay, that's simplify the equation that we have here. This is the R we have right here, this R multiplied by here, become this R here. Conductivity, therefore now we have this, again, we have to integrate this part. If I integrate this one, become R dt over the R, and if you integrate this one, become 1 over R squared plus a constant. Therefore, that's become this one, okay? Now we can go back and then divide again by R and integrate it one more time. Then we find the temperature distribution within the thickness of the pipe. Any questions so far, please?
What was the value of K already? I
K mentioned,
take it.
mentioned, we can come back and tell you K is 14 watt.
Okay, perfect.
Okay.
Thank you.
No problem, sir. Therefore, now we get this far, we go one more time and integrate, and then this becomes this one. Therefore, now he asks us to find the temperature distribution within the thickness of the pipe. Now I have two constant here, C1 and C2, but I have two boundary conditions. At R equal 1, temperature is this. At R equal 2, temperature that. Therefore, I know this two value of R and we have two constant. I can replace it here and we find this two. At R1, the temperature was 60 degrees here. At R2, it was 80 degrees. This one here. Therefore, we have two equations and two unknown. And from here, we can calculate the value of C1 and C2. And this is the value. Okay. Any question?
Sir,
Yes, sir.
could we also have used a different boundary condition of thermal symmetry in this case also? Or
What do you mean by thermal symmetry, sir?
where at the midpoint of the cylinder, it's dt over dr equals 0?
We can find you can find that too. Yes, we can find
Okay.
that but again, since the two values given, that's the easiest one to do that.
Okay.
You mean you go back to this equation here, and you can say dt over dr is equal to 0
Yes.
at which r?
Because at the middle of this, at the midpoint of the cylinder, we have the boundary condition of where dt over dr equals 0 because of thermal symmetry. So what I would do
Is
is
it not my question? I answered fast. Is it thermal symmetry? Because one side is at 60 degrees and the other side is 80
Oh,
degrees.
okay. No,
Cannot be used. That
yeah, you're right.
Okay.
Thank you.
Sir,
Yes, sir.
if we consider the first equation on top of the page,
Yes.
we consider dt over dr at R1, then dt over dr is 0, since there's no difference in temperature, it's just one temperature.
Zero? Why is 0, sir? Because you
Because
have
at one point, there's only one temperature at that one point, right?
no. Let's go back to the figure here. Do you have a figure? No, we don't have the figure. Okay. You have a cylinder, right?
Yeah.
A cylinder. The question, what do you mean? I have I have thermal boundary. Okay. Let me if I can get the figure here. Okay. Okay, this is cylinder, but this has a thickness.
Yep.
Okay, it has a thickness. Inside the boundary is mentioned at R equal 15. Therefore, this is the inside diameter. Inside diameter is exposed to fluid passing to the is 60 degrees. And outside the pipe is exposed to indoor environment is 80 degrees. Therefore, there is no symmetry here.
Yeah, I'm not talking about symmetry.
Yes. What the question you're saying?
I'm asking if you go on the next page, yeah, the one on top.
Yes.
If we take dt over dr equals this, can we take dt over dr at R1 is 0?
Now the question here is why dt over r is equal to 0?
So it's 60.
It's 60 degrees. The temperature is
Okay.
60. But the dt over the r is not 0.
Okay, because it makes me like when I see dt over dr, it's a difference in temperature over a dr, so a difference in
No,
radius.
it is mentioning, if you look at here, it's mentioned dt over dr at r equal this is equal conduction is passing to the wall.
Okay.
Therefore, dt over dr cannot be 0.
So if we evaluate this equation at R1, we put Egen R1 over 2K plus C1 over R1 equals 60.
That's exactly what we have here.
I know, but I was wondering if you could do it without integrating a second time and having C2 at the same time.
Because we do not have any information about we know dt over dr is not 0 because there is a temperature gradient between inside the pipe and outside the pipe.
Yes.
And that's representing the variation of the temperature within the solid.
Because in some of the exercises that I've done in chapter 2, sometimes they take dt over dr, dt at R1, and they put either 0 because we know that at that point it's 0.
That's depend on what exactly the problem is asking you. For
Okay.
example, if I mention to you the pipe is perfectly insulated at R equal 2.
Yeah, there's no gradient in there.
That's right. Therefore, dt over dr is equal 0.
Okay.
Here we are
Alright.
looking about the thickness of the pipe.
Yes.
Talking about thickness of the pipe, and the thickness of the pipe, there is a 2 different temperature.
Okay.
The temperature at the center cannot be 0 because it shows we have conduction to the thickness of the duct.
All right.
That's
Thank you.
representing variation of the temperature within the thickness of the pipe. Okay, let's go back to see what we are. They ask us obtain a general relation for the temperature distribution inside the pipe under steady and determine the temperature at the center of the thickness plane of the pipe. Okay, therefore you have to calculate here. And the idea was first to learn how to calculate each generation divided by the volume that give you here. The rest is mathematics. You take integrate, and you have 2 boundary condition, and 2 boundary condition, you place it here, and you find an expression for the temperature here. Now you have a temperature as a function of R. Yeah, okay. Change different at R equals 0. If you put R equal 15, you have to get this one, and if you put R equal 20, you have to get this value. Okay. Now he's asking you what is the temperature at the middle. Therefore, one side is 15 centimeter, the other side is 20. The average, the middle becomes 17.5. Therefore, if in this equation you put 17.5 centimeter, you will find the temperature at the center of the thickness of the pipe. Therefore, the temperature at the center surface of the pipe is determined at this radius. If you put this in this expression that you have here, R is square and R. Okay, it shows that energy goes from 80 to inside, from outside of the pipe to inside, and somewhere in the center of the pipe, the temperature is 71.3. Any question?
Sure. When it says the center of the pipe, it doesn't mean like one radius is 0?
No, because this expression, good question, this expression that you obtain based on these 2 boundary conditions is only valid for the thickness of the pipe.
Okay.
Okay, very good question. Therefore, this expression is only applicable inside the material of the pipe, not the place that fluid is passed. It's only correct between this radius and this radius. Okay, therefore we put at the center. I will mention here, if you remember, it mentioned, let me go back, I'm sorry again. At the center plane of the pipe. Here, that word here, this word here, it means only about the thickness of the pipe, okay? Very good. Now look at, you know you have the solution. Go back just for 1 minute. Look at your solution and see where you made mistake. And if you have any question, please do ask me. Okay? Because the whole idea would let you learn from your mistake, where you make mistake, okay? Check your question, your solution that you have, if you have done it in the paper, and just go through it fast and find out where that mistake was made.
Sir,
Yes, sir.
do you are we gonna do any question from chapter 7 today?
That was not the question. The question here, do you have any question about this problem, sir? We come back to that question, that solution.
No. My question is about something else.
Oh, yeah, that's, we come back to that one. We have still another lecture left, okay?
Okay.
No question?
Somebody's trying to talk, I think.
Yes, I'm trying to hear. Please ask the question. Okay, if not, let's move to the next one. 2 parallel disc of diameter 0.5 meter. And I made a mistake because I put the number over there, and you know that it's from chapter 13. 2 parallel disc of diameter 0.6 meter separated by L.4 on the top of each other. Well, both discs are black, that means something, and maintain a temperature of 450. Therefore, both of them are the same temperature. The black side of the disk are insulated, and the environment that the disk are in can be considered to be black body at 300 degrees. Determine the net rate of radiation heat transfer from the disk to environment. Therefore, you have two parallel disks, and you can see the environment outside. First, trying to visualize what is the problem. Unfortunately, I mentioned this is chapter 13, therefore you can see this is radiation. Now, try to put the procedure that you're going to follow to answer this question. What information is given? What information you have to answer? And the step you have to do that one, okay? Any suggestion? Therefore, we have two parallel plate, but this is not an enclosure. Enclosure is the room that is at the temperature of 300 degrees. Therefore, we have two surface disk. The distance is 40 centimeter apart, but they are at temperature of 450. Therefore, they are radiating to outside. If you look at the figure, is like this. You have a disk up here and bottom here insulated. The temperature of the two plate is 450, and mentions black body. Therefore, emissivity is equal 1. And this inside a room at the temperature of 300 degree Kelvin. And that's, again, we assume this environment is black body. I believe the question here is how much energy emitted from this surface and went out. We are not interested from 1 to 2 or from 2 to 1. We are interested in how much energy comes from this surface and the top surface to the environment outside. If therefore easy, you can, since you know the radius and you know the distance,
Sir,
you can go and, yes, sir.
can we calculate the view factor
Yeah,
first,
yes,
and then see whatever is not going to that surface goes to the environment?
absolutely. Therefore, you calculate
Okay.
View factor from 1 to 2 or 2 to 1. You can use the figure that you have in your textbook. And if you do that, you can see that that's, I believe, is equal to this one. But now also you can use the summation from 1 to 1, 1 to 2, 1 to 3. And then you can see 1 to 1 is equal 0. Therefore, 1 to 2, you calculate it from the figure. And therefore, this is from 1 to the environment is open. Radiation coming out from here to outside, radiation coming here to outside, radiation from here to outside. Therefore, now, since you know the temperature here is 450, and you know the temperature environment, the surrounding is 300 degree, you can easily write the energy exchange between the disk 1 or disk 2 to environment. But since there are two of them, you can multiply by 2. Therefore, you can say the Q3 is equal 1 to 3 and 2 to 3. Since they are symmetric, they are the same temperature, 450, 450, you can calculate one of them and multiply them by 2. These two represent one from this surface and one from this surface, okay? And therefore, this is shape factor we find from 1 to 3. This is exactly from 1 to 3. This is surface 1 to 3. But since 2 to 3 is symmetric, that's why we put 2 here. Okay, if we calculate how much energy emitted by the disk and transmitted to the environment, 781. Okay. Any question here, please?
Sir,
Yes, sir.
You mentioned that the summation rule can only be applied for an enclosure.
That's correct.
So for this case, you considered it as an enclosure because you defined the environment to be a black body at 300 Kelvin?
No, the reason here, as I mentioned here, is we assume this to disk inside the room that you're sitting. Right now, you're sitting inside the room, right?
Right.
All right. Therefore, I assume this to diskette is inside this room, and is asking you how much is energy come from this surface and emitted to the wall of your room. Therefore, I place this one inside an enclosure because this environment, it means the wall of in your room.
Okay.
Okay.
Yeah.
Therefore, I did not write the summation root for these two. I put a boundary here, and that's, let's look at here, how much energy goes from this border out, how much is going from here out, okay? Did you get it?
Yeah, thank you.
Please. Okay, now you have your solution, and we have it here. Check your solution and check the solution we have, and ask me any question that you have. Why, if you did it correctly, fantastic, but if you use another technique, like, let's have some discussion, okay? Here, the reason, look at here, is if I assume here is one line here. Okay. The reason that okay. Let's assume this is a complete cylinder, right? And this is whatever leaves from this surface, and this surface comes to that environment. Therefore, I assume this is an enclosure, a cylinder enclosure, right? Therefore, there's energy exchange between disk 1 and disk 2, and between disk 1 and 3. And 3 is the sides, exactly the same problem that we did last lecture, okay? Whatever leave this surface, and this surface going to that environment, okay? Therefore, this shape factor of 1 to 3, I use this one as enclosure here, okay? As enclosure, 1, 2, and this green one represent 3, okay? And whatever leave from this surface is going to be exposed, exchanging energy with a surface of 300 degree. It's okay? Is it clear?
Yes.
Good. Let's do this problem. Now, since I put number 6, therefore you know it's from chapter 6, okay? Take your time and do it all the way to the end again. Do it all the way to the end to make sure that you really understood the problem and you don't have any problem in the exam. Any question? I believe this was easy. Therefore, it's chapter 6, and we are talking about airflow over a flat plate. It mentioned the velocity, mentioned at what temperature the air is coming. Therefore, we can use this information to look at the physical property of the air at that temperature. Mention what plate length should be used to achieve a Reynolds number of this one. Unknown here is the length of the paper, the length of the plate. Therefore, we can know the Reynolds number. We know the physical property. We can place it and find the length of the plate, okay? Therefore, here is the solution. Here is the kinematic, viscosity, and so on. We know that. And the Reynolds number we would like to reach is 10 to the power 8. And we put it in this equation. Here is Reynolds number equal this. We know the viscosity. We know the Reynolds number. The airflow rate is being given. Therefore, the length of the plate, in order to reach that Reynolds number, remember, in the case of flow over a plate, the Reynolds number is a function of length of the plate. As we increase the length of the paper, plate, the Reynolds number will increase. Therefore, we find if the plate is 39 meters, the Reynolds number reach 10 to the power 8. Therefore, this is the first part of the question. The first part of the question was, what should be the plate length in order to reach that one? Okay. Now, if the critical Reynolds number, again, we know that the critical number is the number, the flow change from laminar to turbulent, okay? And that's 500,000, okay? If the critical Reynolds number will be 500, what should be the length of the plate? At what distance from the beginning at x equals 0, that Reynolds number reaches that number? Again, we go back and we use the same equation, but in this time, we know the critical number is 500,000. And what this is again, remember we're talking about airflow over a flat plate. The Reynolds number is a function of the length, okay? In the case of pipe, it's not, okay? Therefore, the critical length become almost 0.19. It means almost 19 centimeter. After 19 centimeter here, the flow becomes turbulent. And here is the turbulent, okay? Any question? Any question? Something you have to keep in mind when we are talking about airflow over a plate.
Sir?
The characteristic length is the length of the plate. Yes, sir.
In one of the exercises that I've done, sometimes the Reynolds number is above 10 to the 7, but they still take the equation, which includes turbulent flow. How much can we allow that
Again,
if it's above?
You mentioned 10 to the power 7. It is turbulent, sir.
I know, but the equation, when we use it, it says from 500,000 to 10 to the 7. But if it's above 10 to the 7, are we just considering turbulent and we use the equation anyways, or it's because they had to fix a limit to the use of that formula?
I believe in your textbook you gave some other equation that is applied for longer length, okay? But check your textbook. I believe there are some other equations that give you for longer Reynolds number. But in case you're solving a problem that in your textbook you don't have appropriate equation, you can mention the assumption, I'm using this equation because I don't have another thing. But there are, I believe there are in your textbook, there was also some other equation that for longer length of the plate. Okay. Therefore, now we learn at least, again, the whole idea here, it was to remind you what is the critical length, and to remind you, in the case of flow over flat plate, the Reynolds number is a function of length of the plate. Any question? Any suggestion, any discussion? No, let me go to next one. Any question? As you notice, it's come from chapter 6. What is given and what procedure we should use and what the question is asking you. Is asking you to calculate the surface temperature gradient. Okay, therefore we have a sort of plate, stainless steel. It's giving you the thickness of that plate. Is going through the furnace with the speed of 1 centimeter per second. The air temperature in the furnace is around 900 degrees, and the convective heat transfer within the furnace is around 80 watt. Now, if we assume the furnace length is 3 meters, okay, the question is asking you what is the temperature gradient at the surface. Does anyone want to suggest?
We have to start by the bio number.
Okay, I calculate bio number. What should I do with bio number?
Well, we determine if it's a lump system or not, and then using the speed, we find how long it takes to get to the middle of the furnace.
Excellent, excellent, excellent. Therefore, as she suggests, it mentioned the temperature, initial temperature is 20. Enter in the furnace, the environment is 300 degrees, and it moves with the velocity of 1 meter per second. The question we are trying to find out how long that plate will remain inside the furnace. And based on that one, we can calculate the temperature, okay? Therefore, that's fantastic, very good. Therefore, we know this physical property of the steel, okay? Then we can calculate is a plate, but we know that the thickness is 5, therefore since it's symmetric, because both sides of the plate exposed to the furnace, therefore here the thickness, the characteristic leg is half of the thickness is 2.5 millimeter. And then we calculate the Boyer number, and Boyer number is very small, as she mentioned. We can assume this is lump system, therefore we can assume everywhere inside the plate is the same temperature. Okay, therefore its temperature at the surface is the same as the temperature at the center. Therefore that's lumps approach. Therefore this you can see this less than 0.1. We can make that assumption, and now we have an expression, equation easy, that we can calculate the information we needed, okay? In order to do that, if you look at this equation here, we know here is the initial temperature. This is the temperature of the furnace, and we're trying to calculate the temperature function of time, and the time is right here, okay? And B is only characteristic parameter, HA times the mass times the density. And since we have all the information, we know the convective heat transfer, we know the density of the plate, the specific heat, and also characteristic length, we can calculate dV is equal here. Now we have B value, we can go calculate also T, because we mentioned what is the length and what is the speed. A speed, okay, divided by length, it gives us the time, the length, okay, the time. We mentioned 3 meters, okay, and this is 0.1, we can calculate this value, okay. Go through the procedure and let me know if you have any question. We have this information. We can go back. We know the temperature infinite. We mentioned here. We mentioned this one. All of them is known. We calculate the B. We calculate the time. Therefore, we place it here. We can find this one. Therefore, the temperature everywhere in the plate, because we use lump, everywhere in the plate is around 592. Okay, but the question was asking something else. Okay, the question was asking here is determine the surface temperature gradient of this, the surface temperature gradient. Okay, the surface temperature gradient. Surface, how can I do this one?
Well, we have an equation for the gradient.
Yes.
The gradient at x equals 1.5 would be minus h over k times the temperature difference.
Excellent. Therefore, we go back and we calculate this temperature gradient. Therefore, we mentioned the conduction through the plate is convected to outside. Conduction, this represents the conduction heat transfer, Fourier. And since the steady state is equal with convection. Therefore, we know this one right here. We know infinity, we know h, we know k. Therefore, this is temperature gradient at the surface. Temperature gradient at the surface. And easily can be calculated based here. H is given, and all information is given. Therefore, we can calculate this become this one. Therefore, okay. Therefore, the idea here is slowly we have to be able to analyze the problem and trying to see what information is given, what is needed, what assumption that we can make, and trying to solve the problem. Therefore, it takes some time. Read every problem in the exam, read them carefully, trying to understand, and then start to do the solution, okay? Because something comes to your mind, don't go, no, this is the procedure I'm going to follow. I'm doing this, then I do this, then I do this one, and that's the shortest way to get to the solution, okay? Any question, please? Let's go back to somebody asked something about chapter 7. What do you want to know about chapter 7, sir?
Let me find the question. One
okay,
second.
Let me find another question for you. Let's do this one then. Look at here. This is air is to be cooled in evaporator section of refrigerator by passing over a bank of 0.8 centimeter diameter pipe at minus 20 degree. Air approach the tube bank in the normal direction. Therefore, air goes perpendicular. These are the pipe is going, and this perpendicular this one. The velocity is given is 5 meters per second. The tubes are arranged in line. Therefore, in line, it means like the distance for all of them, x and y direction are the same. Therefore, longitude and transverse are the same spacing, 1.5 centimeter. Okay, this is the distance, and this is the diameter of the pipe. Okay, there are 25 rows in the flow direction. Therefore, as if air goes, it has to pass 25 tube. Determine the refrigeration capacity of the system and pressure drop across the tube. As we mentioned before, when we're dealing with the bank of tube, we know the velocity is 5 meters per second, but this is before reach the tubes. When we would like to pass the tubes, now the area will change. As the area will change, the velocity will change, and the velocity become maximum. Therefore, in this case, we have to calculate the maximum velocity that air is exposed, in contact with the tube. Therefore, Before it was 5 meters per second, but now it's passing over this tube, the velocity is higher. And the Reynolds number we calculate is based on the maximum velocity. We know the spacing, we know the diameter, and we know the velocity. Therefore, we can easily calculate the maximum velocity. Please do it slowly, and then I will discuss it.
Sir, I have
Yes,
a
sir.
question. I have a question, but it's for the previous example. You said that you took the conductivity of the
Plate.
of the plate instead of the fluid.
So again, good question. We mentioned right here, discussing right here, right? This equal, right?
Yeah.
Because I'm talking about conduction through the plate. Remember,
Yeah.
we're talking about the still plate.
Yeah.
We are interested in the conduction inside the plate.
Okay.
And then not the temperature gradient in the air. We are interested in the
Plate.
the
Okay.
plate. That's right.
Okay. Thank you.
Sure thing. We know the spacing here. Remember, we can calculate the maximum velocity. We have an equation, and that we can use that equation to calculate the maximum velocity, and that depends on the d and the spacing between these two plates. Okay. Okay. Please do the calc step by step. Write it down. Then we can discuss the problem together. One more minute. Okay, therefore, we need to calculate the capacity of the refrigeration system. It simply means trying to calculate how much energy has been transferred from the air to tube, okay? We have the temperature air is coming here, evaporator section tube, refrigerator passing over bank of tube. The temperature of the tube is -20. Air is coming in with the temperature of 0 and velocity of 5 meters per second. Therefore, from here, we can calculate the maximum velocity. And from maximum velocity, we can calculate Reynolds number. And from Reynolds number, we can find out which correlation should we use to do that, based on the table as given in the textbook, okay? Since we know the spacing and also we know it's in line, okay? And for the procedure we follow here is as this, in line, right here, transverse, longitude, and diameter is given. This number is given, the temperature is -20, 5 meters per second. Therefore, we can look at the physical property of the air. Since we do not know that what temperature is leaving, we can assume the value of the property at mean temperature -5. Remember that the air is coming at 0 degree and the temperature of the tube was -20, okay? Therefore, we can assume the air is leaving is -10. Therefore, we can calculate the mean temperature of the physical property. Again, this we always have to come back and verify. Let's go back again. Just remember, the temperature of the tube was -20 and is leaving and coming in at 0 degree. Therefore, the temperature cannot be more than -20, okay? Less than -20. Therefore, it has to be between 0 and this. Therefore, we select what temperature and we try to verify that assumption. And that's exactly what we did here, okay?
How do we select it, sir?
Say it again.
How did you choose -5? Just randomly?
Again, we use some of our basic knowledge. It's coming in at 0 degree, right?
Yes.
And the mean, again, if the length of my heat exchanger would be infinite, the temperature is leaving is become -20, but it's not. It's a certain length, okay? Therefore, it has to be sort of more than -20, okay? You can assume it is -15. You can assume -10 and select something in that range, okay? Or -5. And then you have to come and verify that number, okay? Therefore, your temperature air is living is something between 0 and -20. Definitely will not be -20 because then the length of your heat exchanger become infinite. If you remember that figure in chapter 8, that you have a fixed temperature and the temperature is coming in and moving exponentially, okay? Therefore, you can assume it's -15, 0 and -15 become -7.5, and you can calculate the physical property -7.5. You can assume it's -8. Therefore, something has to be in that range. But again, you have to come and verify it. It doesn't mean we are going to be correct. You have to come and verify it. Therefore, that's where, so I assume the temperature is living is -10, 0 -10 divided by 2 become -5. And then we are going to calculate the maximum velocity. We have an expression, and that expression that we have ST and velocity, and therefore the velocity is air is passing over the tube. The velocity of air is passing over the tube is 10.7 meters per second. It's coming here before reach the tube. When reach the tube, the open area become less, therefore the velocity will increase. Okay, this, remember this equation you obtain by writing a simple mass balance. Okay, and now we have this, we have all the physical property, and we go and we calculate a Reynolds number. Okay, Reynolds number, remember, as this is diameter, because air over the tube, the characteristic length is diameter. Therefore, this become your Reynolds number. And now, based on this Reynolds number, you go back and look at the table of this, that you have. And look at here, this my Reynolds number is in line, and you find appropriate. Let me go back if I have it here. No, I don't have it, unfortunately, here. You have a table. Okay, we had a hard look here. We are supposed to have it right here. Therefore, you have a table in your textbook that you can look at on that table and find appropriate correlation. Okay, and the table is 7.1. Okay, okay, right here. Okay, therefore you have that correlation. This is in line right here. You are talking about 6,000 something like that. Therefore, 4 in this range. Therefore, this becomes the correlation that you have to use. Okay. The correlation that you use, table 7.2 in your textbook. Okay. Now we find here. We go back. Which problem was I solving here? I forgot even which problem was it. Okay, I would change too many slides. That's fine. Okay. Therefore, this problem we're solving here, 5 meter, and based on that correlation, we find this one. This comes from 7.1 right here, 7.2, and that's your Nusselt number, and that's why we calculated also the Prandtl number at the surface temperature, here. Therefore, we have this Reynolds number, Prandtl number at the mean temperature, Prandtl number at the surface temperature of the tube, -20. That was, if you don't remember, let me go back again, right here, this one. Again, remember, it mentioned the number of the line is 25. Therefore, since the number is more than 16, there is no need for correction. If it was 10, we have to go and make the correction. There's no need for correction. And since we know the Reynolds Nusselt number, we can calculate the heat transfer coefficient. Therefore, that's the value of heat transfer coefficient. Now we can go back we know the H, we know the temperature difference, and we know the number of the tube. We can calculate the energy exchange. Any question? Therefore, now we know the number of the tube, the total tube. Okay. These are the total tube. Therefore, become N times H times area times delta T. And that's, we can calculate this one. Okay. This is the surface area. This is for one tube. And since we have 375 tube, we multiply that one. This is the length. This is the diameter, this pi. And we can calculate the mass flow rate. Do you know why we calculate the mass flow rate? Why? Okay, let me go back and ask you what is the question. He's asking you calculate the capacity. How can I calculate the capacity? In order to calculate the capacity, what should I do? Okay, think about that. Therefore, we need to calculate the exit temperature. That's we calculate the exit temperature here based on this expression that we have. Okay, because the temperature is constant, air coming in slowly as move on, the temperature difference become less. Therefore, we have to calculate the mean temperature that we need, the delta T, in order to use it. Q equal N A H delta T. Since the temperature of the pipe is constant, the difference temperature between air and surface become less and less. Therefore, we use log mean temperature. Use log mean temperature, and that's become here, and that's your Q. Your Q becomes this value. H A, this is the total area of the pipe that we calculate. We multiply by N. H, we had it. The delta T, as I mentioned, because the temperature difference between the fluid and the surface, the temperature difference is slowly becoming. Therefore, the temperature of the air goes inside, it changes exponentially. Okay. Therefore, we have to calculate the log mean temperature. That's why we have to come here to calculate the mass flow rate. Okay. Any question, please? Okay, then they have to go and calculate the pressure drop. Pressure drop, again, delta P. It's very easy to calculate, but you have to use the table because, again, you have to find those psi and F to calculate the delta P. We know the Reynolds number. We know all of this. We go to table 7.2 to calculate from figure to that, and that's your delta P. Now, what should I do next now? He asked me to calculate the Q, I calculate. He asked me to calculate the delta P, I did calculation. What else do I have to do now? What else do I need to do? Louder.
To verify the temperature.
I have to verify the temperature. That's correct, sir. Let's go back. We find the temperature is minus 13, right? And if I calculate minus 13, 0 minus 13 divided by 2 becomes 6.5, 6.8. Therefore, we can see I only made 1 degree. The temperature will be different, okay? And 1 degree, the physical property will not change dramatically, okay? Therefore, here we are safe. We don't need to go back and to verify it, okay? The aromatic mean temperature, it was minus 6.9, therefore we are safe, okay? Because N coming in 0, leaving, we calculate was 13.7, divided by 2 is 6.9. We assume is minus 5, here is minus 7, therefore we can see is not that big difference that we can, if you go back and look at the physical property at -7, it's not that much difference for -5. Therefore, we are safe, okay? Therefore, we do not need. If I made -20, then I had some problem, okay? But again, depend on the problem. Any question, ladies and gentlemen?
Sorry, I didn't get where did we use the mass flow rate?
When we calculate the exit temperature, sir, here to calculate the exit temperature, we have to use this X1 here. Because in order for me to calculate the log mean temperature, I need to know the temperatures coming in, I need the temperature of the surface, I need to know the exit temperature. Therefore, in order to calculate the exit temperature, we have to use this equation. Because the temperature as air goes in, change exponentially, okay? Therefore, here, this equation that we use to calculate the exit temperature. Okay,
Okay, thank you.
sure. Okay, gentlemen, ladies and gentlemen, thank you very much. I will try to prepare more questions. Please read, please study. And Thursday, we are going to solve another 4 or 5 questions. But the only time this exercise is good if you have went through the chapter, studied the chapter, and when we are giving you some time, you also do it on the paper. That way we can make sure that you can see your mistake and you will not repeat that mistake again. Okay? Thank you again. All the best. Then see you on Thursday.
Sir?
Yes, sir.
I have a question concerning the same question about the steel.
Before you ask me a question, before you leave, ladies and gentlemen, I raised your concern with the university, and they sort of find out that there was some too many sort of discussion during the exam, and now they train invigilator that there will be less communication, less distraction. Therefore, that I raised your concern, I discussed with them, and they're implementing that idea. And there are some other students, they need some special arrangement. And they was told that you contacted directly with that office, that they're trying to place you in different sort of room, okay? There will be less disturbance and less discussion. Therefore, yes, I pass your message to the people responsible. And they mentioned they have trained the invigilator and they're trying to be as quiet as possible. And those students with the special need also to try to place them in separate room, that to be less disturbance. Okay, I forgot. Now, sir, I come back to your question, sir.
Yeah, it was concerning the question from chapter 6 about the steel plate going into a furnace.
Yes.
You mentioned that we used the conductivity K of the steel.
Yes.
To find the temperature gradient within the steel.
Yes.
But didn't we just say that it was a lump sum? So all the temperature within the steel is the same. So delta T would just be 0.
That's correct. But they mentioned at the surface, when you would like to calculate how much energy passed through that plate, how do you calculate? The conduction through the plate, okay? Therefore, the convection comes to the surface and goes through the plate. Okay?
Yeah, through the plate. Okay.
Okay.
So you just do K again.
Yeah.
Oh, okay.
Anyway, please study. Please, you have 1 more 2 days time, practice, and I try to come with another 5, 6 questions for next lecture that we go through it. Please bring your calculator, paper, and formula sheet to make sure that you have all the information there, okay? As we agree, 4 pages of formula sheets, okay? Thank you very much. Have a nice evening.